Welcome back. Do you like to watch football? Are you male or female? Would knowing your gender have helped me guess the answer to the first question? Well, if the results are similar for men and women, then whether one likes football is independent of whether you're male or female. But I'll bet if I asked whether you like to shop for clothing, the results would be dramatically different for men and women, making it a dependent relationship. Not all data can be averaged. That doesn't mean we can't analyze it. Think of all the analysis that pollsters do in determining how a Democrat versus a Republican will answer a question or whether an issue is truly bipartisan. This is the power of chi-square testing. And it opens up the door to analyzing surveys and finding answers to questions like whether one's job satisfaction is truly related to his or her pay. Or maybe it's linked to whether his office has a great view or whether her boss gives her pats on the back. Get the inside scoop. Come inside.
Chi-square testing. Well, in this unit, we're going to address hypothesis tests when your variables are only categorical. This is actually one of the simplest techniques to apply and a very common and popular one because quite often that's the data we have. When we're analyzing survey results, polling results, all kinds of data, we'll find that the most appropriate tool is the chi-square test. People seem to jump on t-tests for everything. It turns out this is actually one of the most applicable tests there are, and as I indicated, it's actually one of the easier ones to do. If you had to do it by hand, you could very easily do it. There's two general groupings of chi-square tests, depending on whether or not we're dealing with one variable or two variables. When we're dealing with one, they typically call it a goodness of fit test. When we're dealing with two, we call it a test of independence. But both of them involve the exact same computations. We just take a slightly different setup on both approaches. Let's start with the goodness of fit test. Whenever you may have heard, read, whatever, about a distribution appearing normally distributed or looking normally distributed, there are tests that could be done with software where we can determine whether or not it fits a normal distribution. If you were to flip a coin, you would expect half of the time to get heads and half of the time to get tails. Now, if you don't get exactly 50-50 split, it doesn't mean you've got a bad coin. If you flipped it 10 times and got 6 heads and 4 tails, you're hardly likely to say, my God, this coin's defective. Let me get another one in place of it. On the other hand, if you flipped it 100 times and got 95 heads and 5 tails, you'd be suspicious the coin was bent or something. So what we're testing for is not that the coin is perfect. You could never prove perfection. We're testing for the opposite, whether or not it's clearly not a fair coin. This is actually the techniques applied in Las Vegas and in Atlantic City and all kinds of casinos. Nowadays, they have so much technology in those places. They look for patterns. And what they're actually testing for is to see whether or not a distribution doesn't fit with what is expected. They know what they expect to see, and if what they see doesn't match what they expect to see, that's when they start monitoring those tables and games even harder. If you watch a roulette game, well, there's 38 numbers on the roulette wheel. 18 are red and 18 are black, mixed in there from 1 through 36. And then there's a 0 and a double 0 that are both green. So 38 possible numbers. Spin that ball around that roulette wheel. You'd expect that roughly 47% of the time it'll come up red, 47% of the time it'll come up black, and the other 5% of the time it'll come up green. So if they're watching and they see that it's coming up green, 0, double 0, 10 or 20% of the time, that's going to raise a red flag. Something's going on. Or if it's coming up red 60% of the time, that's going to raise a flag. Something's going on. They don't expect it to be a perfect match to what's expected, but it should be relatively close. So what they're really asking is, does the distribution of what we got fit with what we expected to get? And fit gives a little bit of a range of error where it's still okay, not something that would make you wonder if someone's cheating. Same way watching a person play. In a game like blackjack, that's up to a person's abilities and a person's risk. They make decisions. So we can't say we expect them to lose a certain number of games and win a certain number of games. We understand that they could win more than they lose based on how they play. But if they are playing a game like roulette where it's 100% based on chance, and all their betting are reds and blacks, odds and evens, whatever, we expect they should win roughly 47% of the time. If a person's winning 75% of their time on a roulette wheel, we know they're probably cheating because it just doesn't fit. So Vegas does that quite often. They're looking for, does the distribution of what we actually see fit with what we expect to see? That is the cornerstone of everything we're going to be doing in this unit. Well, even with the distributions like the normal distribution, you will often see where tests are done to see if data fits a normal distribution, because it is required in some tests that the data be normally distributed. And while we can't prove that it's perfectly normal, we can prove if it's far from normal. So we're looking to see, the null hypothesis is that it fits the normal distribution. The alternate is that it doesn't fit. And if it's a far cry from what we would expect to see in a normal distribution, we reject the null and say, sorry, you failed the assumption of normality. You're going to have to choose a non-parametric test. So there's a lot of statistical software packages that do that, where they do a chi-square goodness of fit test, and you can say, I want to check it against whatever distribution you want, normal being the most common one, and it'll tell you whether it fits that pattern. This is actually very popular. In another Vegas one to throw out there, dice. You expect to see dice rolls occur in a certain pattern in what we call a triangular distribution. If you roll 2 dice, you expect that 6 out of every 36 rolls should come up 7, 2 out of every 36 rolls should come up 11, so that would mean 8 out of 36 times a person would roll 7 or 11 on the first roll and get an automatic win. And you'd expect 4 out of 36 times a person would get craps on the first roll, rolling a 2, 3, or 12, and they know what they should expect to see. And so they're going to count those percentages, see how often is this and that coming up. If it doesn't match, they're going to figure the dice must be loaded. So they don't just go out and accuse. They get data first. And the data, if it's substantial and it shows something that the distribution does not fit, that is considered evidence by the Gaming Commission, which would allow them to do such investigation. They're not just going to accuse you, break your arms, throw you in jail or whatever. They need proof that you actually cheated, but it does give them enough reason to suspect and to investigate, and so they would put monitors, and focus so much more attention on whoever it is that's doing, that's cheating or potentially cheating. If we look at the first screen display here, this one is chi-square goodness of fit, assuming equal expected. What that means is, for this particular spreadsheet, if we expect an even distribution, in other words, the same amount of each of the items, we can use this particular worksheet. If we expect that they're different, there's another worksheet to cover that. So if you're flipping a coin, for a fair coin, you expect the same number of heads and tails. So this one's just going to save us a step because it's going to compute the expected values for us. If you flipped a coin 100 times and got 59 heads and 41 tails, you type those numbers in. The spreadsheet's saying, well, 59 plus 41 equals 100. And since there's 2 of them, that means we expected 50 of each. So it automatically populates the 50-50. And the way chi-square is calculated is quite simple. It just says, what was the observed, 59, what was the expected, 50. The difference between those two is 9. The observed minus the expected. And then we square them. We square it to kind of take care of the pluses and minuses. We square it. That makes it 81. We then divide it by the expected value. And the expected value in this case is 50. 81 divided by 50 is 1.62. That kind of brings it down to earth, because the problem is that observed minus expected could get blown out of proportion. It is all relative. Is it a big number? Is it a small number? Is relative. So dividing it by the expected brings it down to a normalized level, you might say. So we calculated for each value. For heads, we calculated a chi-square of 1.62 because the difference was 9 for an expected of 50. We did the same for tails. We add the 2 up, and it gives us a total combined chi-square test statistic of 3.24. Well, if we looked up a table of chi-square values, it would tell us this magical cutoff. It says if it's above this number, since you only have 2 items here, if it's above this number, then you would say reject the null. Obviously, it's way off. And that number happens to be 3.84. But you don't have to worry about that stuff. Just like all the other hypothesis tests we did, The only thing you have to concern yourself with is the p-value. And the p-value in this case is 0.0719, which is greater than 0.05. So do not reject the null hypothesis. We do not have enough evidence to suggest something's wrong here. Even though it's close, doesn't matter. Close isn't good enough. It has to be clear-cut. If I flip a coin 100 times, that's a perfectly fair coin. There's a 7% chance that I could get 59 heads and 41 tails from a perfectly fair coin. So I'd have no reason to truly suspect that it's a bad coin. If it was below 0.05, be a different story. Then I would have reason to suspect it. So on the next slide, you see what would happen if I had gotten 60 heads and 40 tails. Completely different. That slight change made the p-value drop to 0.0455. Well, now the probability of getting that kind of result randomly is less than 5%. We now have enough evidence to suggest that that coin is not fair. So we would say reject the null, conclude the coin is not fair, that the distribution of coin flips does not fit with the distribution from a perfectly fair coin. And just to point out that it's not the size of the proportions that really matter. Look at the next slide. You see if I put in 3 heads and 1 tail, well, 75% of the time the flip was heads and 25% tails. That seems really lopsided. Should be 50-50, but it's based on so few coin flips that the chi-square value is really small, the p-value is really large, and we say, sorry, not enough evidence there. On the other hand, you could say, well, 51% is nothing to really get bothered by. So, okay, what if we flipped it 10,000 times and got 5,100 heads and 4,900 tails? That's 51% heads, 49% tails. Hardly sounds like much of a difference, yet it turns out to be significant. So it just shows you can't jump to conclusions by saying that percent is really big, reject the null, or that percent is really, it's really close to 50%, do not reject the null. You could see firsthand how one that was clearly larger wasn't significant and one that was really close was. Because it was based on so much data or so little data. It is a combination of the two. The larger the disproportionate amount is, the less data you need. So yeah, if you had 75% heads, it might only take 10 coin flips before you're convinced something's wrong. But if you have 51% heads, it might take 10,000 to convince you something's wrong. But the point is it needs both pieces of information to really say something. On the next slide, you see another example is with dice rolls. If I roll a single die, you expect to see an even number of 1s, 2s, 3s, up to 6s. And so here, if I rolled it 120 times, typed in all my observed, you could see that it just calculated, well, that means you expected 20 per. And based on that, it comes out and says, oh no, this is definitely not a fair coin. Well, 13 1s, 33 2s, you got a whole lot more 2s than expected, a lot fewer 1s than expected. The 6s don't bother me so much. The 5s, that's astronomical to get 36 of them. So you can see they're all over the place. You see a pattern like that, it would definitely draw suspicion. But with this test, you can confirm it. Here that p-value is 0, saying the likelihood that you could take a perfectly fair die and roll it and get that kind of result is 0%. It's not going to happen. So now we have enough evidence to suggest something is wrong with the dice rolls. I don't care who's rolling the dice. You should see something closer to, 18 to 22 rolls per instead of 33, 36, 7. It shouldn't be that disproportionate if it were perfectly fair. You might have an occasional flare-up. Things happen. Weird streaks happen, but it shouldn't be that out of whack. And as I said, all they're going to do is give them reasons to investigate. You can't accuse someone of cheating because you see this, but you could certainly suspect it and then dig even more. This is a hypothesis test to just see whether or not we should dig further. Now, what if we don't expect equal distributions? Not a problem. We just have to type in one extra column. Let's go back to that roulette wheel. We expected to see about 47% reds, 47% blacks, and the rest greens. So let's suppose we spun it 200 times and got 100 red, 80 black, 20 green. We expected those percents. We put those in there, and then Excel does the rest, and it says, well, you've rolled it 200 times, 47.37% of that is 94.74, and it calculates all the rest. So it says, okay, you got 100 reds, you expected 94.7. You got 80 blacks, you expected 94.7. You expected 20 greens and got 10.53. Calculate the chi-square value, and you get a p-value of 0.0039, which is far less than 0.05. So we would reject the null and say that the sample of roulette rolls does not fit with a fair roulette wheel. That's what we're testing. It doesn't fit. We haven't proven it's bad, but we are seeing that it just does not fit with what is fair. The green ones really were what threw it off the most. If we had gotten closer to 12, 13, 14 maybe, it would have been fine, but to get 20 when we expected 10, that caused the chi-square to really blow up. And the house may love that one because hardly anybody ever bets on green, so that gives the house reason to collect. But the Gaming Commission would surely come down on them if they give themselves an unfair edge. So they need to play fair by the Gaming Commission's rules, and then they make sure that you play fair because they're businessmen and they don't want to lose money to cheaters. Okay, so we looked at the chi-square goodness of fit. Now let's look at the chi-square test of independence. For this one, we have to actually have two variables, both of them being categorical in nature. And it is okay if one of them is ordinal, as long as it has very few values to it. Like Likert scales on surveys, if you have strongly agree, disagree, strongly disagree, you have very limited values. That's fine. Or you can regroup them, like we did in pivot tables, where you can just have positive and negative for the response. That's fine too. As long as there's limited values, it would work just fine. Even if you had to use a scale one, if you said number of classes students take and everyone's taking either 1, 2, or 3 classes and that's it. In the MBA program, you don't see people taking much more than that. You could get away with it because there's so few values. But for the most part, this tool is used on categorical data. What we're really looking for here, it's not really so much a fit, even though we're doing the calculations the same way. We're looking for relationships between two variables. We create what we call a cross-tabulation, which is where we're displaying the information of two variables across from each other. And we did this in the probability tables, and this is really the same thing. We're just testing for something else. Like in an example here, if I were to ask men and women, do you like to shop for shoes? And I had 100 men surveyed and 200 women surveyed. And of the 100 men, 90 said no. And of the 200 women, 150 said no. So we had 90% of the men said no, and 75% of the women said no. What we want to know is, does the answer to that question matter or depend on one's gender? Does knowing that the person is male or female change the answer? So we're asking if there's a dependent relationship between the two. So if I said, how do you think the person answered? And you're like, what if I told you it was a man? What if I told you it was a woman? If your answer is going to be drastically different, then you know that there's probably a relationship there. So that's what we're actually testing for. When you load the data into the chi-square table, as you can see, in the yellow area, you loaded the numbers. In the blue area below, it's actually calculating the expected frequencies. Now, there were 300 people surveyed altogether. Of the 300, 60 said yes, and 240 said no. Well, 60 out of 300 is 20%. That means if there was no relationship, no dependence on gender, we should see 20% of the men said yes, and 20% of the women said yes. Well, of the 100 men, we should have seen 20 yeses and 80 nos. Of the 200 women, we should have seen 40 yeses and 160 nos. But we got the numbers that you see. So to calculate it, we would just take each observed and each expected and say, well, we got 10 men who said yes, should have gotten 20. Calculate the chi-square for that. We got 90 men who said no, should have gotten 80. Calculated for that. So we would do observed minus expected, squared over expected, and so on. Add them all up and calculate our chi-square statistic and then our p-value. And the p-value here is less than 0.05. It's 0.0022, which is definitely significantly less than 0.05. We would reject the null. So my hypothesis in this case is one's enjoyment of shoe shopping is independent of one's gender. I would expect to get the same answer whether the person is a male or female. The alternate is that it's dependent. I expect different answers based on whether they're male or female. And since I rejected the null, I'm clearly saying, yeah, there's definitely a dependency. A significantly larger percentage of women like to shop for shoes than do men. Both of them had a majority say no, but it doesn't matter. The answer I get does depend on whether it's a male or a female. Like if I told you the answer was no, guess if it was male or female, you would probably say it's probably male. If I told them the answer is yes, you'd say, well, it's probably a female. And why not? Because almost all the yeses came from women. So it would make sense to do that. Obviously, gender is a factor in that particular instance. What if the question was, do you like to watch football? Surveyed 100 men, 80 said yes. Surveyed 200 women, 140 said yes. So I had 80% of the men, 70% of the women. That's 10% difference. Question is it a significant difference? Follow the exact same routine. If you type the numbers in there, it's going to calculate the expected frequencies and do the comparisons. Comes up with a p-value of 0.0648. Well, 0.0648 is slightly larger than 0.05, which is good enough to say, do not reject the null. So we have insufficient evidence to conclude that one's enjoyment of football depends on one's gender. Even though there was a larger percentage of the men than the women, that could just be sampling error. We don't have reason to suspect it would be different. We would basically say one's love of football is independent of whether the person is a male or a female. A very popular use of this tool is with polls. Whether it be employee surveys or election polls. I'm always looking at the election poll results to see how people voted on an issue and were they Democrat or Republican, were they this, were they that. It's interesting to see what kind of results you get. If a person tends to go to church, they vote this way on this issue, and politicians take advantage of that because that helps them with their marketing. If they find out that a person is more likely to vote for them if they are belonging to a biker group or carrying a Bible or whatever, that may affect how they market themselves to that group. If they find it doesn't seem to matter, we got 52% support in this group, 52% support in that group, it doesn't really matter. Then they'll say, oh, well, then we won't worry about that. But if it turns out that a certain thing is a factor, like I'm more likely to get votes if I have my wife with me than if I don't have my wife with me, so it seems to matter to these people, they'll say, well, you're coming along because it seems to be dependent. Their vote depends on you being there. They look at this data. They're analysts that are watching everything. It's almost a staged game. They plan all the moves accordingly, and they use these polls to give them that necessary information so that they can make the right decisions. So we actually govern what next moves they're going to make by our actions. Let's look at a routine survey. When I was analyzing employee surveys at one point, I looked at ones for a hospital, and there were many, many questions, maybe 30, 40, 50 questions, I forget what. We asked them questions like, are you satisfied with the job? Do you like your boss? Whatever. It went on and on and on, but they're typical standard employee survey questions. And in the past, whenever they analyzed the data, the common approach was just to rank order from lowest to highest, what got the worst scores, what got the best scores. And year after year, the worst score always came from, are you satisfied with your pay? Who's going to say yes? I mean, short of a person who just got promoted, who's excited, not many people are going to say, yeah, I love my pay. I don't need any more. I'm satisfied. Because that's how it might sound to them. They don't want to tell them, hey, this is good enough for me. You can pass it on to someone else. So more often than not, a lot more often, they're going to answer no. Well, 95% of the people in this particular group said they were not satisfied with their pay. And that was always ranked highest, and the hospital would say, well, what are we going to do about it? Well, you could say give everybody a pay raise. That'll make them happy. Well, statistically, research that's been done has shown that giving a pay raise only works for up to one pay period, and then people go back to being their unhappy selves. So that's not really the answer. What I did is I took the overall satisfaction question. How satisfied are you with working here? Would you recommend it to a friend? I forget the exact wording, but one that was the real key question. And then I cross-tabulated it with all the others. I just used my pivot table tool and ran all the cross-tabulations, and then I did a chi-square test on these. What I found, interestingly, was what you see here. When I cross-tabulated pay satisfaction with overall satisfaction, the 50 people who said they were happy with their pay, 40 of those 50 said they loved it there. Of the 950 who said they were not happy with their pay, 720 said they loved it there. So overall, 76% of the people said they loved working there. 80% of the people who loved their pay loved it. 70-some-odd% of the people who didn't love their pay loved working there. doesn't sound like it's really much of a difference, and it turns out it wasn't. The p-value is 0.4968, which is a lot larger than 0.05, and we don't reject the no. We're basically saying one's satisfaction with their job at this place is really independent of their pay. We could give them more money. It's not going to change anything. Because heck, if 80% of the people who are satisfied with their pay love it here, and 70-some-odd% of the people who aren't satisfied still love it here, giving them more money is not likely to change anything, really. On the other hand, when I looked at questions about, I love my boss, I'm treated with respect, they value my opinion, all the softer type questions got a completely different result. On the question, am I treated with respect? Well, they never gave a thought to that question as being an issue, because 80% of the people said yes. Well, if 80% said they're treated with respect, we don't have a problem. What was funny is the questions that they thought they didn't have a problem with because they got high scores turned out to be the biggest problems, and the ones like pay and benefits, which got the low scores, turned out to not be the problems. Because look what I've uncovered. Of the 800 people who felt they were treated with respect, 750, which is like 94%, said, yes, I'm very satisfied with my job here. Of the 200 people who said they weren't treated with respect, only 10 said they loved their job, which is 5%. 94% of the people who were treated with respect loved it there. 5% of the people who weren't treated with respect loved it there. So 760 total people said they loved it there. And that means you would expect 76% of each group. Well, we expected to see 76% of the people who felt they were treated with respect saying they were satisfied. A lot more than that said it, 94%. Virtually everyone who said they were treated with respect said, I love it here. And even on the more extreme end, 95% of the people who said they were not treated with respect said they don't like it here. That is as extreme as you get. The p-value turned out to be 0. I had no problems rejecting the null hypothesis there, and I clearly concluded that one's overall satisfaction truly depended on whether or not one was treated with respect. I found that to be the case on all the softer questions. I like my boss, I'm valued here, and so on. All the soft questions turned out to be statistically significant, and we showed a dependent relationship. And all the harder ones, the more concrete ones about pay, benefits, parking, office size, and whatnot, even though they got the worst overall scores, not one of them was significant. When I showed it to them, they thought, in the past we were always told these are the things we need to work on, and now they realize what they need to do is make sure that people are treated better, valued more, and whatever, made to feel good, and the satisfaction scores would go up. And don't spend your time and money and energy taking care of improving parking and whatever, because it's not going to change anything since one had nothing to do with the other. They found that to be a real eye-opener, and all I did was a simple cross-tabulation. So it is truly a powerful tool. Whether you're just looking at polling results, like I said, or completed surveys or whatnot, it is probably the most used tool when it comes to analyzing that type of data. You'd be amazed what you'll find when you look at it. And so that wraps up Unit 6. In the next unit, we're going to go into correlation and regression. In there, we're looking at what happens when the variables are both scale, interval ratio. And we'll even touch on multiple regression, which is where we have 3 or more variables, and then you can have nominal variables thrown in there too. So you can throw tons of variables in, and the intent there is to learn how to do forecasting, how to take data you have and predict what the value of another variable is going to be based on what you see.